Let us take a look at the diffusion coefficient of carbon in alpha ion. We call it ferrite versus in gamma ion. Sometimes people call it austenite. Alpha ion and gamma ion, if you study material science, you would know alpha ion exists at for ion or Fe from room temperature, low temperature, all the way to up to around 700 or slightly higher, while gamma ion is the phase for ion that is about 700 to 1000 all the way to around 1500. Alpha ion, as we said, is in BCC structure, body-centered cubic structure, while gamma ion is in the so-called FCC or face-centered cubic crystal structure. And what people observed in history is that it appears that diffusion coefficient of carbon appears to be 100 times higher in alpha ion than in gamma ion. In another way, at the same temperature, the carbon diffused in this BCC ion at about 100 times of that in FCC ion. That's what people observe. To illustrate that, I'm borrowing an old graph from literature, actually pretty old. The vertical axis is D for diffusion coefficient, and it's in the unit of meter square per second, which is also very common. And the horizontal axis, we can plot it in two ways. The bottom one is for inverse of temperature normalized by melting temperature, while the top one is for the actual temperature. Of course, the inverse temperature, the larger this 1 over T means the lower the temperature, while the smaller the 1 over T, the higher the temperature. So on this plot, the right side is for lower temperature, the left side is for higher temperature, and the vertical axis is diffusion coefficient. And naturally, the diffusion coefficient is lower when the temperature is lower, and it gets higher when the temperature gets higher. Okay, and then you see that in this plot, the temperature is divided into three regions. From low temperature all the way roughly to 900 degrees C, we are in so-called alpha ion or the so-called BCC, body-centered cubic ion. Fe, while above 900 something all the way to 1400 something, we are in the so-called gamma ion or FCC, face-centered cubic ion. And above this around 1400 degrees C, the material strangely changes back to delta ion, which is again body-centered cubic ion. The exact rhythm for this change between alpha to gamma to delta is beyond this course, but you just keep in mind alpha is for BCC, gamma is for FCC, okay? And here what people observed is that, okay, different people studied the diffusion coefficient and plotted them up, and this paper summarized the result from different studies. And you see that, okay, for alpha ion, it's generally in this band, while for gamma ion, it's generally in this band. But you see that at the transition temperature, of around 900, probably 10 to 920 degrees C, you see that at this same temperature, the diffusion coefficient in alpha ion or in BCC ion is about 2 orders magnitude than if the ion is gamma phase or FCC. This gap, this sudden change, as the temperature changes, there's a sudden change in diffusion coefficient accompanied by the phase change from alpha to gamma, from BCC to FCC. Okay? So that's what people observed. And specifically, if we say at 910 degrees C, for the two systems, one is carbon in alpha ion, the other one is carbon in gamma ion. If you plot the trend and as what we got before, we can get the pre-exponential factor d0 as well as Q for diffusion activation energy. We can get those two numbers for the two different scenarios, carbon in alpha or BCC, carbon in gamma or FCC. And what you see is that the activation energy for carbon in alpha ion is much lower, about half of that in gamma ion, while the pre-exponential factor in alpha is actually much smaller than in gamma. Okay? So that's what people observed the diffusion coefficient at different temperature, and then when you plot it up according Arrhenius relationship, you can extract the diffusion activation energy Q as well as the pre-exponential term D0. Okay? Which are listed here for the two scenario. And then to explain this big difference at the same temperature between the diffusion coefficient, people often mention the so-called closure packing for gamma ion. Closure packing for this FCC gamma ion is cited. For example, in one places, as I read it, the reason for this huge difference of what? Difference in diffusion coefficient between the two different phases of ion lies in the fact that the BCC structure, the alpha ion, the BCC structure is more open and than the gamma ion or the FCC, and the diffusion process in this alpha ion or BCC structure requires less lattice distortion or entropy or thermodynamically favored. That's kind of a hand-waving explanation for this phenomenon. But here in this class, we want to go slightly deeper to look into the difference in diffusion coefficient for the same carbon element but in different crystal structure of ion. Alpha versus gamma, BCC versus FCC. Okay. So now let's look at the crystal structure a little bit. From your introductory materials engineering class, hopefully you remember that atoms in BCC structure packs less dense than atoms in FCC structure. Here, in this table, we list the two different crystal structure, BCC versus FCC. And from your introduction to materials engineering class, you know that's the packing density, how dense the atoms pack in different structure is different. In the BCC structure, the packing density is only 0.68 or 68%, while the packing density is 0.74 or 74% in the FCC structure. What this means is that within for a given volume, in BCC structure, only 68% of the volume is actually occupied by the atoms. The rest, 32%, is just the gap between atoms. In comparison, for FCC, 74% of the volume is actually occupied by the atoms, while the remaining 26% is occupied by the gap between atoms. Okay, also called interstitial between atoms. And if in basic crystallography or introduction to material engineering, we we also know that the ratio of the radius of largest tetrahedral interstitial atom to the host atom are at different ratio. Here for BCC, if you put an impurity atom into the so-called tetrahedral interstitial, the largest of that impurity atom is around the 29% of the host atom. In comparison, if we are looking at FCC structure, if we put a impurity atom into the same tetrahedral site, okay? The largest impurity atom you can fit in there is around 22%, 0.5% of the host atom. That's about tetrahedral site. But in the crystal, typically there's also another type of so-called interstitial or weak interstitial site, which means between the atoms, which we call octahedral site. And for the octahedral site, within the BCC structure, the largest impurity atom that people can fit into a BCC structure is only 15% of the host atom in terms of the radius ratio, while for the FCC structure, you can fit a much larger impurity atom. The impurity atom radius ratio to the host is 41%. Okay, these are what you hopefully would learn from your basic materials engineering or crystallography that tells somewhat different. It tells us the BC structure packs less dense compared with the FCC, and in terms of the uh, impurity size that you can fit into so-called tetrahedral site versus octahedral site. Okay? But researchers have found out that for these two types of ion, BCC versus FCC, or alpha versus gamma, people find that carbon as an impurity in iron always stays in the so-called octahedral site. Octahedral site. Okay? Despite the fact that carbon as an impurity, the octahedral site is much smaller in the alpha ion. You see, the size ratio, the radius ratio for the largest octahedral site is only 0.15 versus the host site, which is much smaller than in the BCC host site. And what this means is that the carbon, if they are going to reside in the octahedral interstitial site, they really have to push the surrounding atoms in order for it to fit in this octahedral site. But from careful study by X-ray, people do find that at least 85% of the carbon atoms occupy octahedral interstitials, even for the BCC structure, even for the situation that the octahedral site opening is actually not big. Okay, with that in mind, now let's look at within the crystal how many so-called interstitial sites are there. From crystal structure, hopefully you learn that the number of tetrahedral sites per unit cell is 12 in the BCC structure. It's only 8 in the FCC structure. And when you normalize that by considering how many atoms within the BCC structure, hopefully you haven't forgot, within the BCC unit cell, there are 2 atoms. So if there are totally 12 interstitial sites, per host atom is only 12 divided by 2, which is 6 interstitial tetrahedral site per host atoms. In comparison, for FCC crystal structure, each unit cell has 4 atoms. So if a unit cell totally has 8 interstitial tetrahedral site, per atom it's only 2 tetrahedral sites. That's for tetrahedral site. And when we consider the so-called octahedral sites, octahedral, the numbers are somewhat different, but trend is the same. If we consider per unit cell, within BCC, there are 6 tetrahedral interstitial sites. And put it another way, there are 3 octahedral sites per host atoms. Octahedral interstitial site per host atom. When we consider FCC, there are a total of 4 octahedral interstitial sites within a unit cell, And if we consider a FCC unit cell has on average 4 atoms, then 4 divided by 4, which means on average that's only 1 octahedral site per atom. Okay? So that's another observation. The number density of octahedral interstitial per unit cell or per ion atom is much larger in the BCC than in the FCC. What we say essentially is per unit cell within the BCC, there are 6 interstitial sites, octahedral sites, while in the FCC, there's only 4 octahedral interstitial sites. And the gap is even larger when we consider per host atom. Per ion atom, there are 3 interstitial sites. Okay, well, octahedral site. Well, for FCC, for every ion atom, there's only 1 open interstitial octahedral site. Okay, that's consistent with the packing density. The higher the packing density, the lower the number density of the so-called interstitial octahedral site. The lower the packing density, the higher the octahedral interstitial sites. Okay, so this is what we got when we examine the crystal structure and the opening, the packing density between BCC versus FCC, between alpha ion versus gamma ion. Okay, now let's go to one step further. Still, we are looking at gamma ion versus alpha ion. We said alpha ion has the so-called body-centered cubic structure, while gamma ion has the face-centered cubic structure. Here we are plotting a unit cell within this cube. The solid circle in both cases represent the atoms location, while the open circle in both cases represent the so-called octahedral sites, Okay? And then let's think. For FCC or gamma ion, which is the one on the left, for FCC or for gamma ion on the left, if we have a carbon sitting at the center, which is a interstitial site, okay? In order for it to jump or for diffuse to a neighboring interstitial site, similarly to another octahedral site, I draw it something like this, from the center to a neighboring, for example, to this location. Okay, now let's examine the so-called jumping distance. Do you see that the distance from the center to this location is half of square root of A gamma Fe? Again, A gamma Fe means the lattice parameter, the distance from here to here, or from here to here. That is our A gamma Fe, means the lattice parameter for this unit cell, this cubic unit cell. And the square root of 2 times this lattice parameter gives the phase diagonal from this location to this location, or from this location to this location. And half of this phase diagonal, do you see, it's from here to here, which is the same as from here face center to the corner, which is half of the so-called phase diagonal. Okay, so that is our jumping distance from location, a octahedral interstitial, to a neighboring octahedral interstitial is half of phase diagonal, and the phase diagonal is square root of 2 times the lattice parameter from here to here. Okay, and then what is this square root of 2 times of lattice parameter, which is from here to here? If you examine it carefully, it would be 4 times of the radius of iron atom. Remember, for this FCC, the atoms are touching each other along this phase diagonal, which means this atom is touching the one in the phase center and touching the one in the opposite on the same surface. Which means from here to here, I would have R, 2R, and R, totally 4 of radius of iron. So half times 4 of radius give us the 2 times radius of iron, which means from the octahedral interstitial in the center to a neighboring interstitial, the jumping distance is actually 2 times of the radius of iron. From here to here is the same distance from here to here, and naturally you see it's 2 times of the radius of iron. In comparison, when we examine the so-called the alpha ion or so-called body-centered cubic ion, we have a cube and an additional ion atom is seated right at the center of this cube right here. Okay, now let's examine the jumping distance. We start from this location, which is still a so-called octahedral site, a so-called octahedral interstitial or octahedral vacancy, and it's jumping to its nearest neighbor, its nearest neighboring interstitial or opening site from here to here. Okay, something like that. And you see that the jumping distance from the phase center to the edge center is half of what I write A alpha dash ion. Again, A alpha dash ion means just the lattice parameter for this cube from here to here or from here to here. The jumping distance from the phase center to the edge center is just half of this lattice parameter. Okay? And then we keep the half in the front, and the lattice parameter. The lattice parameter is related to the radius of iron by this relationship of 4 over square root of 3. I'll put it another way. 4 times of radius of iron, 4 times the radius of iron would be equals to square root of 3 times the lattice parameter. You get this relationship when you consider the distance of so-called body diagonal from this location to this location. From this location, one corner, to the complete opposite corner, so-called body diagonal, that would be square root of 3 times the lattice parameter. And because the corner atom is touching the center atoms touching the opposite corner atom, that is totally 4 radius, and that relates the lattice parameter and the radius. And if we simplify this, we would get 2 and 2 cancel, 2 over square root of 3 of radius of iron. Okay, so now we have the so-called jumping distance for both FCC structure iron versus BCC structure iron. And clearly you see the jumping distance in FCC iron is larger than in BCC iron. Actually, these two are related by a factor of square root of 3. By a square root of 3. Okay, the jumping distance in FCC is square root of 3 times the value of the jumping distance in BCC iron. Okay, so in FCC it's jumping, it has to jump much longer, while in BCC it only has to jump much shorter. So this is what we say here. The jumping distance in alpha ion is much shorter than in gamma ion. For here it's much shorter, for here it's much longer. And as a result, this is what I have. In BCC or alpha ion, the jumping distance is much shorter, Well, remember we just said per atom or per unit cell, there are way more so-called openings or interstitial sites. Shorter jump, more openings for carbon in alpha ion. And as a result, no surprise, we would have faster diffusion of carbon in alpha ion than in gamma ion. Because in alpha in here, you have to jump shorter. You don't have to jump as long, and there are more possibility for you to jump. Of course, the diffusion would be faster. Okay? And that provide a more in-depth understanding of why the diffusion coefficient in alpha ion is much faster than in gamma ion at the same temperature. Okay?